So what I'm going to show you is a quick analysis of an oxide growth run in the MPL. And what we did is we grew a wet oxide at 1100 degrees Celsius for 60 minutes on P-type 100 silicon. The other parameters can be found elsewhere. And we pushed them in at 650, ramped up to 1100, stabilized, and then we grew for 60 minutes. Then we purged for 20 and ramped down. So then we did an analysis. And so here's all the Python code for that. All right. So here's the URL to the actual data. All right, which is from the Filmetrics. And you have to make sure that each point lines up properly, otherwise it throws everything off. And actually, I think, yes, by looking at this, I thought there was an extra point, and I think it's this point right here, which is going to throw off my analysis. But anyway, it's Python, so it'll be easy to rerun. Right. And what it does is it takes this data and every like position, every 5 points, every 5 represents a point on the wafer. So that's position 1. Then you go 1, 2, 3, 4, 5. That's position 1 on the next wafer, and so on and so on. And so all it does is you have the 5 positions, and it goes through and extracts the thickness at that particular spot, 1, 2, 3, 4, or 5 on the wafer in question. And then it takes the average of that so we can plot things out. And then we do a linear regression. So if we look at it, right, the first thing it does is an analysis. We had 30 samples. Before it was 31, right? If we always take 5 measurements per wafer, everything should be divisible by 5. And so, yeah, even I had gotten lazy and not fixed that. We have a mean of 4,677 angstroms with a standard deviation, a minimum value, and a maximum value. So that's on every point on the wafer. Nothing's averaged. All right. And so what we now do is we plot out everything. So position 1 is actually the bottom of the wafer in the furnace. And you can see how that varies with wafer number. Position 2 is the middle of the wafer. Position 3 is actually where the flat is, and that's the top of the wafer in the furnace. And 4 and 5 are the left and right hand sides. And then the gray is the average of all of those. And interestingly, that around position 4 and 5, the variance looks kind of smaller. It's very tight compared to the ends. All right. Then you do a linear regression and you get the slope, the intercept, the R-squared, and the p-values, which yeah, it did change by getting rid of that 1 point. It didn't change the results though, which is that even though you can see a line, right, generated, and maybe by eye it looks like it's going up, R-squared is very small, meaning if I have this line, these points are scattered, randomly around it. And then a p-value of 0.6 is greater than 0.05, which means it's very unlikely there's a relationship there. Okay, which is in fact what we want. We would want this actually to be flat and then a tight random variance around it. All right. So of course, now R-squared is 0.27 and 0.06. If you look at my results right now, it's a little bit off. I'll fix that later. But if you notice the inconsistency in the video, it's Really, there's no relationship. That's the big point. Even though we get an equation, right? There's no relationship. Looks like 4 and 5 might be tight, and we might want to look in that later. Um, but yeah, based on the data, this is a pretty good process with only 1.6 variation across the entire run, right? If we wanted a smaller variation, we could be looking at samples, just say, well, we only want these wafers, and then it would be tighter. Now, maybe we need to add more dummies, and we could get it much tighter. So even though there's no relationship, right, like it's getting thicker or thinner over the length of the tube, it doesn't mean we can't try to get the spec a little bit better. Anyway, that's another way to explore it, but um, yeah, we'll just leave it at that. Um, I'll post the link to this worksheet in the description, and I'll fix the typos that you were probably noticing.